Hey Math 1. This is a modified version of the notes that I did for 8.11 in which I'm going to go over some of the other applications, actually the final applications of exponential functions that we'll be talking about. Population growth and decay, appreciation versus depreciation of value, and then radioactivity, half-lives. So, kind of got a lot of concepts in here, but I think you'll see that it's not too much of a stretch to actually determine what we're computing here. So, first thing I'm going to talk about is population growth and population decline. So, I took these two towns/cities that are kind of in our world right now. Cooksville, I'll write that a little bigger for you, and Bloomington. I did some other towns in class already, so that's why I'm focusing on these two in particular. So, population growth. How do we compute it? Well, we first need three pieces of information. One, you gotta know the current population to make any kind of predictions about where it's gonna be in the future. So at the top of this sheet, it all said, predict basically the 2100, and I put AD so that we know we're talking about the year 2100. Yeah. So predict the 2100 AD population of these towns. Well, the first thing you got to know is what's the current Cooksville population? Or at least the best up-to-date estimate of what it is. I went online and I found a pretty reputable source that told me that there is 179 people documented in Cooksville at around 2019. So it's both important to know what the current population is and what date we're actually using to determine that. Number two, we got to know what the growth rate is. What's the growth rate of Cooksville's population? Well, at this particular moment, okay, because the growth rate changes kind of from year to year. It's like, well, if there's a slight little boom in population growth, then it's increasing, it's positive. If there's a decline, if people leave town, then it's going to go down a little bit. It turns out that at that moment when the population was determined, it was in the midst of a minus 1.6% growth rate, which really means it's declining by 1.6%. And then the third thing we need to figure out is how much time passes. How much time are we talking here? Well, we're trying to get to 2100 AD, but we're basing it off of information from 2019. So we wouldn't base it on information from 2021, the current time. We would base it off of 2019. So you're going to say it's 2100 years minus 2019 years. It's 81. So the 179, the negative 1.6%, and the 81 are the three pivotal pieces of information we need. Now, how do we use them? Well, I drew this explanation a lot more out in class. I'm just going to give you guys the bare bones. To get the new population, you take the original or current or principal population, I'm going to call it P, and then you multiply it by 1. You either add if it's growing, subtracting if it's declining, and what you do is you say, I want to subtract the percentage, because the 1 here is kind of like representing 100% of the population. I'm just going to put percent per 100. R divided by 100 is the thing that makes the percentage actually work well with the 1 inside of this grouping symbol. Right? And you take all of that to the t power. That's where the exponential part comes in play. You are taking it not times t, but to the t power. Again, the explanation for this takes a little bit longer, in which I sort of say, what would be the population in 2022, 2023? It'd be much better if we had a formula. That's the formula we came up with. Okay? So the new population. What do we plug in for our original? The original population was 179. That 1 is a constant that never changes. It's always 1 right there. Subtraction, because it's not a growth rate, but a decline rate in this case. Yeah. So minus 1.6 divided by 100. And then you take that, all of that, the whole grouping symbol, to the 81 power. Yeah, then we use our calculators. So I will show you it through the lens of this calculator. Let's see, do I have another version? You know what? You guys will see. So I am literally typing it in exactly as I see it. 179. Then I put the grouping symbols in there. Yeah. 1 minus, and then I'm going to go 1.6. I don't really have a fraction button on this calculator, but division is the same thing as the operation that fractions have. And my calculator knows the order of operations, so it knows to divide before subtracting. I'm going to close off the parentheses and then take it to the, I use the caret button, 81st power. Your caret button might not actually make it look like an exponent. It might just put the caret symbol in there. All right, what do we get? 48.47? Okay, so it's about 48 people. Ah, that's the estimated population of Cooksville in 2100 AD. Which is kind of amazing to think that this seems like a minimal decline rate, right? I mean, it's like, well, we're losing 1.6%. Doesn't seem that significant. Well, over the course of 81 years, if it doesn't change, if it's always just 1.6%, there's only going to be 48 people left in that small town. All right, let's do the exact same thing, but through the lens and information of Bloomington, okay? So I'm going to still predict the population of 2100 AD. I'm still using this model right here. I need to know what is all my information for Bloomington. All right, so Bloomington. Let's get a current population estimate. Right, and from the same source that I went to, I found that Bloomington's population in 2019 was 77,000, let me make sure I get this right, 330. Same year, that was an estimated population. Okay? And 2, the growth rate was ever so slight. The growth rate was a positive 0.9%. Okay? And then again, we need to figure out how much time passes between the start and the desired finish. Well, again, it's 81 years. It's not always going to be 81, obviously, right? Because the data is not always going to come from 2019. But again, you take the end date, subtract the initial information date, and you get 81. So I've got plus 0.9, I've got 81, and I've got 77,300. Those three numbers are going into this formula, and they will give you the predicted population for Bloomington in 2100, 81 years from now. So 77,330. 1, not minus, plus because it is growing, 0.9 divided by 100. And we're taking that to the 81st power. Okay, so we'll go back to the calculator. We got 77,330 times 1 plus 0.9 divided by 100. I think we're going well so far. Close off the symbols. To the 81st power. What's the population of Bloomington going to be? Wow. 159,783.7. I'm going to round it up to 84. Which, this is amazing. You know why this is amazing? Because what it shows is that in 81 years, with just a tiny, teeny tiny constant growth rate, Bloomington Normal is going to double its population, and a little bit more so, with just that growth rate. So you see how this information can really help city planners? Like if Bloomington was growing at a rate of 10% a year, they would reach this number so much quicker. We'd have to figure out, okay, how do we service all these people with water, sewage, garbage collection, ... You know what I mean? So exponential modeling for population growth is actually a kind of a big deal. Okay? And now you guys have a little bit of an understanding of how that works. So, moving on, population growth and decay, pretty straightforward. The next thing we're going to talk about is valuation, so appreciation, things that are increasing in value, depreciation, things that decrease in value. So I'm going to try to zoom in on this here so you guys can see it better. So we're talking car purchases. So I'm just going to throw this out here. For appreciation and depreciation, your model is still the new value equals the principal value times 100% of it. You're either adding for appreciation, subtraction for depreciation, R divided by 100 to the t power. That's the good news. For these types of examples, your model doesn't change. Okay? You just got to piece together what the important pieces of info are. So just yesterday, so we're kind of assuming it's early March 2021. Just yesterday, March 2021, random guy, William, purchased a $16,000 car. This particular model has a yearly depreciation rate of 22%. And Will is basically wondering how much his car will be worth in 2030. So we need to get the principal amount. That was kind of like our first number one. 2, we need to figure out what's the rate of growth or decay, what's the rate of appreciation or depreciation. And then number 3, like what's the time value here? How much time has gone by? Well, the principal amount is $16,000. And it appears we can just plug in the 16,000 without the dollar sign. R is going to be 22%. And then 2030 is the time minus yesterday, March 2021. I'm okay with just calling it 2030. We don't need to get into months and everything. Let's just call it 9 years. Okay. So all of this together, the new price in 2030, how much is the car going to be worth? 16,000 times 1, depreciation means subtraction, 22 over 100 to the 9th power. All right, I'm going to plug that in my calculator. I will, I'll not stick the calculator in your face here, so I'll just do it on my own. 16,000 times 1 minus 22 divided by 100, not 1,000, 100, and take that to the 9th power. Okay, here's what it's worth in 2030. $1,709.90, which seems about right. I mean, that's I had a car of similar value, and after about 9 years, it was maybe it was worth a little bit more. And keep in mind too that these models aren't always like spot on, because some people take really good care of their cars. Some people do not. Some people drive short distances to work and don't really go on long vacations much with their car. Some people commute at least 1 or 2 hours a day, in one day a person can drive over 100 miles to get to their job. So depreciation, of course, doesn't always follow these models the same way. So, I'm going to stop the video here and start a new one for radioactive decay, because, I don't know, I just feel like that's the right thing to do. All right, see you guys.